Okay, this is chapter 13 in our Strength of Materials class, and in this class we're looking at the deflection of beams. So let me start off by drawing a simply supported beam. Got my roller support, got my pin support, and let's say I apply a load to it, maybe a vertical concentrated load at the center. When we load that beam, it is going to bend. And I'm drawing here the dashed line, the sort of shape that it's going to make. This distance right here is deflection. And we use a small delta, lowercase delta, to represent that. So when designing a beam, we want to know how much does the beam deflect. We also, of course, need to make sure it doesn't exceed an allowable stress. But even if the beam is adequately strong against stress, we still want to make sure it doesn't deflect too much. This type of deflection, having too much of it, can result in a bouncy floor. It can result in just a lot of vibration, a lot of motion. It makes someone standing on this floor or maybe driving across a bridge have a sense of unease if there's too much motion occurring. So we need to limit this as well. So we frequently limit the deflection to some multiple of the span length. So if the length of the beam is L, we might limit the maximum deflection to L over 240 or L over 360 are just two common examples of how we might limit the deflection of a beam. So how do we calculate the deflection of a beam? Well, basically, this entire chapter is based on looking up the appropriate formula and applying it. It's really just about that simple. So the formulas can be found in Appendix H in the textbook. So we've got Appendix H. And what Appendix H does is it gives you lots of different support conditions and loading conditions. And you need to essentially find the one that matches the situation in the question that or problem that you're looking at and apply it. So let's look at example 15-3. We have example 15-3 here. And in this example, we have the most common beam and support and loading condition. That is, we have a simply supported beam with a pin and roller support at either end, and we have a uniformly distributed load across the entire length of the beam. I know I'm not drawing this especially well, but hopefully you get the idea. Where the W, the distributed load, is 2,300 pounds per foot, and the span length of the beam is 24 feet, and the beam itself is a W14 by 74. So we want to calculate the maximum deflection. Delta max equals what? Well, we have to go to Appendix H, and I have copied, done a screen capture for Appendix H, the very first number 1 situation is a simple beam or simply supported beam with a uniformly distributed load. And that's what we've got here in this example. So if we want to know the maximum deflection, here in the appendix they're using a capital delta. So I was using a lowercase delta. I guess I should have been using a capital delta. delta max, and it tells us where that's going to occur at midspan, is equal to 5 WL to the fourth over 384 EI. So that's 5 WL to the fourth over 384 EI. So we need to just plug into this formula and find the deflection. But we do have to make sure we're using proper units. So 5 is just 5, and then we've got our W. What was our W? So if we look back here, W is 2,300 pounds per feet. But E, when we look that up in the appendix, is going to be in KSI. And I, when we look that up in an appendix, is going to be inches to the fourth. So it makes sense to convert these units from pounds per foot to kip per inch. So 2,300 pound per foot multiplied by, for every 1,000 pounds, we have 1 kip. And for every 1 foot, we have 12 inches. So the feet and the feet will cancel out, and the pounds will cancel out, and I'll be left with kips per inch. So let's calculate that. And I am getting that is equal to 0.1917 kips per inch. Now the next unit or variable in my equation here is length. I want that to be in inches. It's given to us in the problem statement in feet, so we're going to have to convert. 24 feet. For every 1 foot, there are 12 inches. And so 24 times 12 gives us 288 inches. So if I come back here to my equation, I've got 5 times W, which when converted to kips per inch is 0.1917 kips per inch. And my length, when converted to inches, is 288 inches to the fourth. Don't forget the exponent. That's pretty easy to forget. Divided by 384 times E. E is the modulus of elasticity. And it can be found in the appendix of the book. Let me take a quick look to see which appendix it's in. Looks like it's in Appendix G. So if you look in Appendix G, all varieties of steel, except for stainless steel, according to our textbook, have a modulus of elasticity of 30,000 KSI. And wide flange beams are made from A992 steel, and that, yes, that's 30,000 KSI. Now, the I is the modulus of elasticity. Scroll down here to give me a little bit more room. So recall again that I is the, not modulus of elasticity, the moment of inertia. It is the moment of inertia. And this is going to be found in Appendix A, where we can find information on wide flange beams. So there are 2 moments of inertia about both the x and the y axis. We want the one about the x axis. And so when we look up a W14 by 74, Ix is 795 inches to the fourth is what the moment of inertia about the x-axis is. So that's 795 inches to the fourth. Okay, so we've got all the variables. We just need to simplify this formula to find delta max, which occurs at the center of the beam, is equal to, see here, we've got 5 times 0.1917 times 288 to the fourth, divided by 384, divided by 30,000, divided by 795, and I am getting for this 0.720. Now if we look at our units, we've got kips per inch times inches to the fourth. So the inches go away, and this becomes inches to the third. And down here we also have KSI, kips per square inch, but since it's on the bottom, kips stay on the bottom. They cancel out the kips on top. And I've got inches squared up here now. And then I've got inches to the fourth here, and so 3 plus 2 is 5, take away 4, and what am I left with? Inches. So the inches to the third and the inches squared would give me inches to the fifth, divided by inches to the fourth, leaves me with just regular old inches, which is, after all, what we're trying to find here. How much does it deflect or sag in the middle? 0.72 inches, so about 3/4 of an inch. So is that too much or not? The original problem statement told us that we did not want the deflection to exceed L over 360. L over 360 would be 288 inches divided by 360 inches. So if I calculate that, 288 divided by 360 is 0.8. That's the allowable deflection. The maximum deflection that our beam is going to experience is 0.72, which is less than 0.8. So this is okay. It is acceptable. Okay, so that's basically it. When it comes to finding deflection for a beam, you have to look up the loading and support situation in Appendix H, choose the right formula, plug in the values, make sure you convert your units appropriately, and solve. So the only added complexity is, what do you do if your exact loading situation cannot be found in Appendix H? So one possible solution is that your loading situation is actually a combination of load situations found in Appendix H. In this class, we're only going to be looking at loading situations that are either in Appendix H or can be made up from combinations found in Appendix H. Beyond that, the calculation does get a bit complicated. It can be done, we're just not going to do it. So in the next video, we'll take a look at an example that is made up of a combination of loading situations.